All right. How's everybody today?
Great.
Great, doing well. Okay, fantastic. Love to hear it. Uh, just a couple reminders. Remember, Friday is, of course, the end of the 6 weeks. So tomorrow is the last day if you're wanting to retake anything. I believe the last grades we have would be the correlation coefficient quiz or the second exam from last Thursday. If that applies to you, let me know. I can get you a pass. As long as you're here before 8:05, I can write you a pass. So if it takes longer, that is not an issue. It looks like on Friday, we're going to have ourselves an exit ticket over chi-squared test for independence. We turned the homework in yesterday. If you have that to turn in, you can do so. But it is going to start giving you points for that point bank that I referred to earlier in the week. We'll go ahead and move on and probably be able to hit probability before the middle of October. I think we're on track right now. As far as the internal assessment, what's due on Monday? Okay, you have the outline. Okay, with that, we do need to include some data, whether you collect it yourself or online, site source, whatever the case is. How are those going? Good. Okay. All right.
So hard on that one.
Okay, so Ella is working very hard on hers. Okay. There you go. So diligent. Okay. All right. But if you do have any questions or difficulties, come see me and I'll see if I can help you out with that. But remember, it is due on Monday. So we are going to start the second 6 weeks with several grades because that chi-squared assignment is going to carry into the next 6 weeks. I want to try to get started on that a little ahead of time because the second 6 weeks is only 5 weeks long. So basically, October is the second 6 weeks, and then we're going to be in the third. So it's going fast. All right. So unless there's any questions,
Well, to be fair, this first it's like 7 weeks.
yeah, I mean we'll have some 7 weeks, 6 weeks in the second semester, but the third 6 weeks is also 5 weeks from what I'm told. So it's going to be interesting. We'll see how that works out.
Love the first.
That means you actually have to try. Oh no. All right. Well, we are finally putting statistics aside. Now, it definitely is not the last time we're going to see it. On our next exam for the second 6 weeks, more than likely I'm going to go ahead and place a chi-squared problem on there because it is something that we do want to remember. And we want to continue to spiral back in with the focus activities as we go through because they're going to be really important to us. But now we're starting our next unit. We're talking about logic sets and probability. So this whole introduction is about sets. So what is a set? It's any well-defined list or collection of objects. Okay, any well-defined list or collection of objects is how we go ahead and define a set. Now, for our purposes, I mean, it could be any items. Typically, they're probably going to be numerical values, but they could really be anything. Okay. Now we have some definitions here to go through. Set notation. Sets are denoted with a capital letter. The items, names, objects, or numbers are enclosed by these squiggly brackets here. Now, this curvy E, this is a symbol that we use to denote is an element of, or it can also mean belongs to. There are a couple of different phrases that can accompany that. So just like if you have an equal sign with a slash through it for not equal to, you can do the same thing for this curvy E. So it is not an element of or does not belong to. So we have an example here. Here's a capital letter being the name of this set. So all even numbers. Okay, so therefore 3 does not belong to set A. All right, there's going to be a lot of notation and abbreviations in this particular unit. So give me an even number. 12. So I could make the true statement that 12 does belong to set A. All right. Now this next part right here is what we're referring to as a solution set. Okay. So solution set. This is when you're going to see an expression like this. It's still in the squiggly brackets, but it starts off with X, and it's read all X such that. That's what this vertical bar means. And then what follows is going to be your restriction, basically the definition or whatever the reader needs to know in order to generate that particular set. Now, instead of a vertical bar, you may have seen these in the past, all X with a colon. Okay. You guys know, if I can talk today, does that look familiar? Okay, either of those are acceptable. They're just interchangeable. They both mean such that, and then what follows is the restriction. Okay, so like in this case, all values of x such that x is an odd number. All right, so the empty set, you can actually go ahead and call this the null set, or typically what I like to do is just use the symbol no solution, the 0 with a slash through it. But it is acceptable to go ahead and draw this, actually put squiggly brackets with nothing in between them. Okay, that represents the null, or what we call the empty set. All right. Now, this is a little bit of review back to that first week, so it's been a good month and a half. But we did talk about the classification of numbers. And here, IB was a little different on this. Remember, what was the one group that you've learned previously, but that IB doesn't worry about? Starts with a W. Remember the whole numbers, okay? So the whole numbers have just been combined with the natural numbers, and they're now referred to as the cardinal numbers. Because that was the key difference between the natural and the wholes, was that the wholes had what element? 0. That was the only difference between them. Okay, so Z represents your integers. These are your positive counting numbers, 0 and their opposites. Again, for these two sets right here, very important, no fractions, no decimals. Okay, none are going to be contained in that set. So Q, the rational, this here's a set notation definition. So all values of m such that m equals a over b. So what it's telling you here is that m is written as a fraction where both a and b belong to the set of integers and b is not equal to 0. So basically what we're saying is it's a rational number if it can be written as a fraction. Okay, as long as the denominator is not 0. And then we have all real numbers R, which encompasses our hierarchy. Okay, so let's go ahead and move on with these definitions here. The cardinal number of a set. Whoa. The cardinal number of a set A, N of A. Anybody need help picking something up or what?
I don't know what happened. I don't know. It just exploded.
Was it yours? Oh, okay.
What was it?
Was it a pen? Okay. All right, well now we got it all. We're good. Okay. So let's see, where were we? The cardinal number of a set A, N of A, represents the number of elements in set A, whatever they may be. Elements of set A. Now, a finite set has a countable number of elements. Countable number of elements, and an infinite set has an infinite number of elements. Okay, so the empty set is denoted as what we talked about earlier, either a literal set with nothing in it or the no solution symbol, the empty. Okay. Or what could we call that instead of the empty set? We can also refer to it as the null set. A lot of different ways to go ahead and describe that. Okay, well, let's see what we got here. So we have basically just a little chart kind of comparing what's the proper way to use things after the definition. So the null or empty set, a set that has no elements, okay, by the symbols we've seen. So all x such that x squared plus 1 equals 0, R belongs to the set of reals. Okay, and that kind of makes sense because if you go ahead and take a look at x squared plus 1, if you were to go ahead and graph that, he is infinitely wide. He's a parabola, right? Okay, so any value of x is going to work there. A finite set, a set whose elements can be counted. So this set here only contains 6. Infinite set, a set for which it is impossible to list the elements. So the set all y such that y is a real number. Okay, absolutely is going to have an infinite number of elements. There's no way we could possibly count that. So it would be more verbalized here than actually as a listing. All right. What else do we got? The algebra of sets. Set A is said to be equal to set B if the sets are identical. That is, they contain the same elements. So we say that A equals B. Now, there's a difference between saying two sets are equal and saying that they're equivalent. Set A is said to be equivalent to set B if, what does this notation with the N mean if I put it before a set? Anybody know? That's exactly right. If you put n, and in parentheses the set you're referring to, like n of A here, we're talking about the number of elements in set A. So like if I were to have a set Well, let's say, I'll use a different letter this time. Let's say C is equal to just something easy, 1, 2, 3, and 4. Then I can say the number of elements in set C would be 4. Okay. All right, so there is a difference between being equal and being equivalent. Equal means you have the exact same elements. Okay, basically it's just a duplicate of the set you're working with. Equivalent just means you have the same number of elements. The elements themselves don't have to be exactly the same. Okay, and in fact, this arrow that's going in both directions, what we're going to find out in later lessons, that's equivalence. Those are your if and only if statements. Okay, but we will get there. All right, so there's an example here. Set A is 10, 20, 30, 40, 50. Set B is A, B, C, D, E. Now, between the two vocabulary words that we just looked at, they are equivalent. They are not equal. Remember, equal means they have the exact same elements. Equivalent just means they have the same number of elements. Okay, so they're said to have a one-to-one correspondence. Okay, for every one element here, there is another unique element over there. All right, and now we've got subsets and proper subsets. Okay, so what's a subset? Subset B is a subset of set A if all the elements in set B are contained in set A. So basically what you're talking about here is a group or a set within a larger group, a larger set. Okay, every set is a subset of itself. All right, now when we're talking subset, you'll notice we have the symbol here. It's a sideways U. That tells you we're dealing with a subset, the group within a group, but it's going to have a bar below it. Okay, that's going to be contradictory to what we have when we call a proper subset that has no bar. So if you were to have, like when you're talking about inequalities, you know, if I said x is greater than or equal to 3, okay, that little bar beneath tells you equality. You know, I just stated it in reading out the expression, but the 3 is included in that, right? So when you see this, we're talking about a subset, so that means the group can be a subset of itself. So is everybody kind of okay on the idea of a group within a group? Okay. I can give you a real world example if you're interested. Sure. Okay. Whoever it was out there that said that. Okay. Think about the campus as a whole. I think we've got a little north of 2,000 students on campus. Okay, but only these 30 students, you folks, make up 6th period math studies. See, the entire campus, we're all Lubbock High students, we're all Westerners, but only you folks belong to this group. So you're a subset in the larger group. Okay, you're a group within a group. That's what we're referring to. Does that make sense? Okay. All right. And the only difference between a subset and what we call a proper subset is that a set B is a proper subset of set A if all the elements of B are contained in set A, but the two sets are not the same. A set is not a proper subset of itself. Okay, so you got some examples down here. I do, actually, right behind you. The Chrome cart may just need to be turned on. There's a little button on the side. Okay. All right, so let's see here. Let's say I've got a set with these 3 elements, these 3 colors, green, yellow, and blue. So the following are going to be subsets. Now remember, with a subset, is it okay for the group itself to be considered a subset or not? Yes, it is. So subsets, that's okay. In fact, take a look at how many we have here. What's this one mean? The null or empty set is considered a subset of the sets we're going to work with. Okay, so we have a subset with each of the individual colors, and then we have different combinations of 2, and then we have the set itself, green, yellow, and blue. So how many total do we have? 8. In fact, what it's going to talk about at the bottom of your page, if you want to go ahead and determine how many subsets a group has, you take 2 and then raise it to the power, which is the number of elements you have in your set. So how many elements were in my set here? 3. So 2 cubed gave me 8. So I know there should be 8 subsets. Okay. Now, when you're talking about a proper subset, look at all the examples we have here, but what's missing? Okay, what's missing? There you go, the set itself. That's the big difference between a subset and a proper subset. A proper subset cannot be a subset of itself. You cannot have the original group. In fact, the expression you're going to use to find the number of proper subsets that a set could have, you're going to have 2 to the p power, where p is the number of elements, but you always subtract 1. The 1 being that original set. Okay, yes, ma'am.
So, if I understand this right,
Okay.
green, yellow, and blue are going to encompass the entire set of A, but it can also.
Yeah, so let's consider that my universal set.
Okay.
That's the only colors I have.
Why include the null set?
Because it's still considered a subset even though it's empty. I mean, there's nothing there, but by definition, we can still count it. Okay.
You can't include the full.
Yeah, now you can't include the original if it's a proper subset. The way I always kind of think about it is a subset is always going to be notated with the bar below it. So always think about that as equality. If you see the bar, the original set can be a subset. If you don't see that bar, then it's a proper subset. So you cannot have the original set. Okay. Yes? Oh, it's just, I mean, there's a derivation for this, but it's just a little formula you apply to this. In fact, it's pretty consistent throughout this lesson. When we start making truth tables, you're going to go ahead and do the same thing to figure out how many rows you're going to need. Okay. So I'm not going to worry about deriving it or showing you where it comes from. I'm just going to give you that formula. Okay. All right, good, good, good. Okay, now there are a couple of issues here. Remember, this symbol here, the curvy E, what does that mean? That means is an element of or belongs to. And the sideways U with the bar, is that a subset or a proper subset? That's a subset. So there's correct ways and incorrect ways that you would go ahead and write these. So for example, here I can say an element 2 belongs to a set. Okay? I would go ahead and say that a set 2 is a subset of 1, 2, and 4. Okay? But look at how we wrote those in the third column over here, the incorrect usage. See, if I put brackets around this 2, I'm referring to this as a what now? As a set. So if I'm referring to it as a set, then I want to use the proper notation. We only say that elements belong to a set. And we say that sets are subsets of others. Okay, we have a group within a group. So you wouldn't say that an element is a subset of a larger group. Okay, an element belongs to or a set is a subset of. Okay, is everybody okay with that? Okay. And then here are the formulas that I was just talking about a second ago. Based on the number of elements that are in your set, okay, 2 to the p if it's a regular subset, if it's a proper subset, 2 to the p minus 1. And now we start getting into the nice things, the things you probably are more familiar with. Okay, intersection and union. Do those sound familiar? All right. Okay. Well, the intersection of two sets is a set of elements that they have in common. Okay. And is denoted by the symbol, it's an upside down U. Okay. Now, does anybody know what word is very, very commonly found when you're talking about an intersection? Small little word, starts with the A. And. So I want all of the elements in set A and set B. When you're talking about an intersection, you use the keyword and. Okay. So here's an example. Set A is all my even numbers. Okay, so I can actually go ahead and start to write this out. So all my even numbers, so 2, and we'll just go ahead and say positive because it could also encompass negatives. So 2, 4, 6, 8, ... because that would definitely be an infinite set, right? Okay. And then what's a prime number again? There you go, a number that's only divisible by 1 or itself. Okay. So then we have 2, 3, 5, and then you can keep going, right? Okay. Well, see, what's in this set and in this set? Well, the intersection, the only elements that have both is 2. Okay. So graphically, we're talking about the overlap, What elements do they share? What do they have in common? That's what we're talking about when we say intersection. Okay, now the union is completely different. The union of the two sets is a combination of all the elements in both sets. Okay, I always like to think about the union as a marriage of the two sets. Okay, I'm going to take everything in set A or set B. I'm going to take them and combine them into one bigger set. What was the key word I used there? Or. So every time you see and, you're going to be talking about an intersection, but every time you're talking about a union, you're going to say or. Okay? And if the capital upside down U is our symbol for an intersection, what's the symbol for a union? A U. And actually, there are, again, multiple symbols that you could be given. For an intersection, instead of a capital upside down U, you could have a capital upside down V. Okay? Yeah, and there are multiple others. These are the most common ones, though. So what's another symbol for union? The normal capital V. Okay. All right. So let's look at this example right here. Bless you. Okay, so set A is the letters in the words mathematics. B is equal to A, B, C, D, E. All right. So the union is to take every letter that I already have in the first set, M-A-T-H-E-M-A-T-I-C-S, and combine it with these over here. So does set B have any letters or elements that the other one does not? Okay. It doesn't have the B or the D. But you'll notice when you look at the union, it has all those letters with those. Okay. And you'll also notice something interesting. How many A's does mathematics, for example, have? 2. So if you have an element that repeats, you don't have to repeat it when you're writing the union. You would just go ahead and list it once. Okay. Questions? All righty. Well, the number of elements in a union of two sets. This is an important concept in set theory. So the number of elements in the union is going to equal the number of elements in set A plus the number of elements in set B minus what? What am I subtracting there? The number of elements in the intersection. Yes. There we go. Because potentially if you go ahead and take a union of two sets, they could potentially have common elements. So if you're looking for the exact number, you want to make sure to subtract the number of elements that duplicate themselves. So that way you get an actual value. Okay, now complement is a big idea here. Complements of sets and the universal set. The universal set's always denoted by a capital U. Okay, the complement of set A is all of the elements that are in the universal set, but not in set A. All right, the complement of A is denoted by A, and you might notice that is, you might say prime, it's a little tick mark. So when you see a set that has that little tick mark where a power should be, we're talking about the complement. Okay. Now, let's take a look at an example here. Let's say the universe is all the letters in the word universal. Okay. So let's say that set A only has A, E, and I. Well, do you notice anything comparing that to the complement? It doesn't have the A, E, or I in a complement. Okay. When you're talking about the complement, you're looking for every element that's still in your universe, but not in that particular set. Okay. So let me give you maybe another example to kind of make it a little more concrete for you. If I go ahead and say that the universe, okay, is equal to, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Let's say the universe only consists of these 10 elements. And let's say that set A is made up of 2, 3, 7, and 10. Okay. What I'm looking for is the complement of A. So I would want every element that's in the universe, but not in A. Okay. So what's an element that's in U, but not in A? 1, 4, there you go. That's what the complement is. It's everything in the universe, but not in that particular set. Okay. So this next part is probably going to make sense. Okay. What's that capital U mean? Union. So if I take the union of A and its complement, it should give me what? The universe. So imagine if I took all the elements from A and combined it into a brand new set with all the elements from A complement. Well, wouldn't that just give me the universe? Okay. Well, let's see here. What's that capital upside down U? So it's telling me if I take the intersection of A and its complement, I'm going to get what? Okay, the empty set, the null set, whatever it is you want to call it. Well, that kind of makes sense because the intersection is only what the two sets share. So what's in set A that's also in A complement? Nothing. That's why we get the null set. Okay. Any questions? Easy, easy, easy. Okay. Good. All right. And then we have this last idea here. The number of elements in set A plus the number of elements in the complement of A should equal the number of elements in the universe. And again, if you compare it to the example I just looked at, we should get 10. Okay, because I only created a universe of 10. Okay. Now, we're going to go ahead and start looking at some shading here. Disjoint sets. Sets are disjoint if they have no elements in common. Okay, so that also could refer to the intersection of two sets if it's empty or null. Okay. Intersecting sets, sets with elements in common. Okay, you're looking for the overlap region. A subset, a set within a set, we describe that as a group within a group. This one doesn't come up too often, but it comes up enough that you definitely want to be familiar with it. It's called the difference. And you go ahead and use a backward slash, okay, in order to notate it. But A backward slash B, this is the set of all elements in A, but not in B. So you'll notice graphically, it just gives you that little crescent region. Okay. Because what's this region right here in the middle? Isn't that still in A? But what's wrong with that? Okay. It is in A, but it's also in B. Okay. And by definition, we want the elements in A, but not in B. Okay. So there's a lot of vocabulary coming your way today. Is there any questions about anything I've talked about? Jacob, how you doing?
Good, sir.
He's good. Okay. All right. So let's do some shading. Let's go ahead and take these two. Now you'll notice below, for number 1, you're going to take the intersection of these three. I want you to show me graphically where the intersection would be on those three. And then I want you to do the same thing for number 2. Okay? Exact same sets, but now we're taking the what? We're taking the union. Okay? So let's practice that. Okay? So shade these 6 the way you believe they should be. That's it. That's good. Okay. So far, so good. Okay. All right. Okay, so I'll just start going around the classroom and ask a few folks to tell me where I should shade. Or would the people I call, would they just want to come on up and show me the shading? I felt as though I could hear a pin drop after I asked them. Okay. All right, how about we start with Noah? Okay, help me out, sir. So this set of disjoint sets, okay, I want the intersection. Where would I shade? You don't. Okay. Remember, The intersection says what's in set A that's also in set B, but I mean, they are called disjoint, and visually I see that the sets are not what? Yeah, they're not connected. They're not overlapping at all. So there's no place to shade there. Okay. Well, what about intersecting sets? What if they do overlap? Ella, where's the intersection? It's just right here in the middle. Okay. What's in set B and in set A? Okay. Well, Lizzie, what would you think about this last one? A group within a group we call subset. What's the intersection? Shade all of B. That's right. There you go. Because the intersection of a subset and a larger set would just be that subset. You're looking for what's contained in both. How are we doing so far? How many people have gotten all three of those right? Ooh, not everybody's hand's going up. Is there anything I can do? Okay. Maybe in a minute. Okay. Number 2, let's take the union. All right. So I want to shade the union of disjoint sets. Erica, what should I shade here? Oh, now, remember, what does union mean? That's the combination, right? So I would shade what? In order to take the union, the sets don't need to have anything in common. They can be completely two different sets, but when I marry them, basically, you just go ahead and create a brand new set based on that. Okay. Let's see, Matthew, can you help me out with the union of intersecting sets? What would I shade here? I'm sorry, sir? He says A and B. Now, when you say A and B, are you talking about the parts that just have A, the parts that just have B, or are we talking about everything? Sure. Okay. All right. Is that what you were referring to? Yes. There you go. So Matthew's right. Okay. The union would be everything in A or B. Remember, the union is or, it's a combination. The intersection is and. That's what they have in common. Okay. So, Emma, finish this one off for me. What would I shade to show the union of subsets? I wouldn't shade it? There is something I would shade.
Just A then?
Just A? So I would just go ahead and shade this?
Well, I'm kind of confused by it because you said A or B.
Yes, one or the other.
Okay, so
So what would that mean here?
I don't know that.
Okay, anybody want to help her out? Is what I have here correct? Partially correct, but what do I need to do? I need to shade B as well. See, that's the difference. Look at the intersecting sets. This right here is the only place I have elements in A and in B. Okay, here, this is where I have everything in A or B. It doesn't matter where it is in the set. We're either combining them through a union or we're finding what they share in the intersection. Okay. All right. So I know what you guys are thinking. Well, those are way too easy. We want something a little more challenging. I hear you. Okay. So now complement and complements an intersection. Okay. So let me give you about a minute, bless you. I'd like you to run through number 3 and show me on disjoint sets what a complement would look like. Then on intersecting sets, on subsets. Then I want you to show me on 4 for those 3. We have some different expressions here. Remember, all these are intersections. Okay. So like that bottom left one right there, That's the intersection of A's complement and B's complement. Okay. All right. And on these, we'll see if we can't get somebody up to the board. Oh, Jacob, you already want to come up?
I just want you to check.
You just want to check? Okay, let me check the first three. Good, 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 good. So Jacob, you could come up and do all of these.
I mean, I could.
He could. So Jacob got all 6 of those right.
Oh, yeah.
Oh.
The Mike Myers
It's been a long time since I've seen that movie.
Such
Yeah.
a good movie.
See, I guess that's the difference, because when you said, oh yeah, my immediate thought was a giant pitcher of Kool-Aid busting through the wall. Oh no. Oh no. Oh yeah. What's that, Emmett?
Everything is just such a mess. Like,
What?
the live action.
Oh. Yeah, some things shouldn't be made live action. Like Aladdin.
Was Aladdin bad?
Speaking of Aladdin,
I was so disappointed when I saw that movie. The one thing I was wanting to see, they didn't do.
Which one?
The live action Aladdin. Now, don't get me wrong, I loved Will Smith. I don't think they used him to his full potential. But the one thing, has anybody not seen the movie? The live action, does anybody care about spoilers?
Nobody.
Okay. I mean, really, if you haven't already seen the cartoon, Disney's just going back for a cash grab on these things.
Probably.
Yeah, I said it. Okay. But the one thing I was really hoping to see at the end was when Jafar becomes the giant serpent. And they didn't do that. The battle was over like... And another thing that annoyed me, I'm sorry, I am not a musical person. They added more songs than was necessary in that
Yeah.
thing. Okay. You know, I get it. Disney's woke. Okay. Uh,
They had work new song.
no, they had extras. Like the one where Jasmine's... What was she was singing about?
Only song.
No, there was more than that, right? Yeah, there was some extra ones, I remember.
Yeah.
Because every time it happened, my eyes got tired from rolling them. I was like, oh, God, here we go again. Okay. Now, don't get me wrong, there were some cool elements there. I like, what they did with Iago. Kind of turning him into the bit. That was kind of cool to see. And I don't know who his name is. I like the guy who played Aladdin. It was pretty cool. I don't know. It's probably one of those movies I would never buy.
Yeah.
Probably not watch again. But I own the animated movie. The animated movie was fantastic. And I don't know, is anybody out there who went to go see The Lion King? How was it?
So disappointed.
It was disappointing?
The CGI was awesome and everything else was
Okay,
awesome.
what else about that one is the part where like when you come to the cloud, it's like remember who you are.
Yeah.
They butchered like that's supposed to be like the most like powerful scene of the whole movie.
But at least it was in the movie? Is there anything from the original that they did not put in? Like, I'm guessing, did Scar still get killed at the
no, they
end?
didn't put in the scene where like Scar and the hyenas are doing the thing.
The thing.
Like he's like singing and the hyenas are like marching.
Oh, okay, yeah.
Because
Yeah.
like the whole point of that scene is they like styled it the way that like people in like the people in the Cold War
Uh-huh.
do their big military parades.
Yeah.
And then they were like that might scare people. And so
They put it in the cartoon.
yeah, and so it was in a cartoon.
Well, also, when was the cartoon made? A couple decades ago. So, yeah. The world was very different then. Okay. Oh my gosh, it's already 2:03.
As cool as it is that they did all that CGI, would have been even cooler to make
Okay.
They did
That
good
CGI
for that.
effort
The time that they were.
Chronicles of Guardian.
But see, you guys are growing up with movies that basically use CGI all the time. I mean, even if you're using CGI, aren't you kind of getting to the point where you can still tell the effect is not real?
Yeah.
Like way back in the day, like go to Star Wars when they used the practical effects.
Yeah.
The models, those look fantastic. You know, way back in the day, a lot of those movies look better than the movies you have nowadays with millions of dollars in the budget. Really? Oh, I thought you were raising your hand. Oh, yeah.
I was babysitting little kids.
Uh-huh.
They're like 6 and 5. And they told me to put on the beats. So I put, like, I looked at
Talking about the live action version?
well, no, like I just assumed they were talking about the cartoon, so I went to see if they could put it in. And they were like, where's the beat? And I was like, what are you talking about? They're like, there's some people, where's the real people? And I was like, I gotta go. They were talking about live action.
Yeah. Well, I mean, so many of the youth today, you know, they're not going to be familiar with the VHS tape
Well, I mean,
or a cassette tape.
we used to watch the VHS tapes in my grandpa's office, like all
In your
the time.
grandpa's office. There he goes. You know what? It brings up a funny story. We're not going to be able to finish this today, so we may as well comment on today's society. Okay, it was last year. Okay, one of my mother's favorite movies was a movie from 1984 called Romancing the Stone
Oh my gosh, I hate that movie.
with Michael Douglas and Kathleen. Why do you hate it? That movie has everything that an amazing 80s movie needs.
Cheesy, it has joy and happiness, sympathy, community,
Anyways. Okay, so has anybody not seen this movie? Okay, so I'm not going to worry about the plot or anything, but suffice it to say that Kathleen Turner's sister gets kidnapped, and she has to deliver the treasure from a map that was found for her life. Okay, so at the beginning of the movie, Kathleen Turner, and you can play this later for your parents if you want to, a little nostalgia. Okay. And they can learn about sets too. But Kathleen Turner is in her apartment. She receives a phone call from the kidnappers telling her what's going on. Okay, she's talking on the phone. My son and I are watching this last year. My son at the time is 9 years old. Okay, and he says, "What is that?" And I said, "What are you talking about?" And he says, "Who is she talking to?" I said, "Well, she's talking on the phone." He said, "That's not a phone." And I said, "Why is that not a phone?" He goes, "Well, what's that wire coming out of it?" See, he has never lived in a world where we had landlines. He's grown up in this technological age with cell phones.
See, anybody born from like 2002 to 2003 is like we still know about this. That's the awkward range.
So we still kind of know.
The forgotten era.
Okay. Okay. All right. That just completely blew me away. You know. All right.